Hello everyone, welcome to ENGR 391 Fluid Mechanics. Over the next several lectures, you will learn fundamental principles that govern how fluids behave, whether they are air, water, or oil. Understanding fluid mechanics is essential for engineers designing pipelines, aircraft, pumps, turbines, and countless other systems. Let's begin with the basics. Mechanics is all that's physical science. It studies how bodies respond to forces. We break it into two categories, statics and dynamic. Statics analyze objects at rest, building, bridges, structural beams. Dynamics examines object in motions, projectiles, rotating machinery, flowing water. And fluid mechanics is our focus. It studies fluids, liquids, and gases, whether they are stationary or moving, and how they interact with solids and each other. What is a fluid anyway? A fluid is any substances in the liquid or gas phase. Here's the key difference between solids and fluids. A solid can resist an applied force by deforming slightly and holding that shape. A fluid is different. Is continuously deformed under any shear force. No matter how small, it cannot resist shear. It flows. So this is water flow in the pipe and air flow around an airplane wing. The distinction is fundamental to everything we do in fluid mechanics. When we apply forces to surfaces, we talk about stress, force per unit area. There are two types: normal stress and shear stress. The normal stress is a force pushing perpendicular to the surface. Think about pressure in a tire. The shear stress is a force pushing parallel or tangentially to the surface. Think of the wind pushing sideways on the building. Pressure is the normal stress in the fluid at rest. And here is important: at rest, shear stress is zero. When you tilt the container or remove support, the fluid begins to move and shears develop. Key differences between liquid and gases. In the liquid, molecules are relatively close together with strong cohesive forces between them. As a result, a liquid takes a shape of its container and forms a free surface. In a gas, molecules are far apart with very weak cohesive forces. As a result, a gas cannot form a free surface in an open container. These differences affect how we analyze flow, pressures, and compressibility. In thermodynamics and fluid mechanics, we define a system as the quantities of matter or region in the space we choose to study. Surroundings is everything outside our system. Boundaries is a real or imaginary line separating them. Why does this matter? Because we will use two different approaches, closed system and open systems, depending on what we are analyzing. Let's see the difference. A closed system is a fixed amount of mass with no mass crossing the boundary. Imagine a seal, balloon, or a piston cylinder device. Energy can move in or out, including heat and work, but the mass inside stays constant. We use closed systems for basic thermodynamics analysis. An open system or control volume is a region in space that we define. Both mass and energy can cross the boundary. Examples for open system include turbines, compressor, pump, jet engines, or pipe with flow. Control surface is the boundaries of control volume. It can be real, like a pipe walls, or imaginary, like an inlet and outlet of a device. Open systems are essential for analyzing flowing fluids, the most common engineering application. Everything in fluid mechanics rests on three conservation laws. Conservation of mass. Mass cannot create or destroy. Instead, it flows mass in equal mass out. The conservation of energy, saying that energy is conserved. We account for kinetic energy, potential energy, pressure energies, and thermal energy. The third law is conservation of momentum. Newton's second law, force equal mass times acceleration. We apply these laws to solve real problems. That's the power of fluid mechanics. An equation of state relates pressure, temperatures, and volume, or in many cases, specific volume, small v, for a substance. The simplest is the ideal gas equation of states. We have this form, where P is absolute pressure, rho is density, R is a gas constant, and T is the absolute temperatures, either in Kelvins or Rankine. This equation tells work well for gases at low pressures and high temperatures. Real gases deviate at high pressure. An example for waters, when water vapors have very high temperatures or low pressure, they become ideal gas. And in this case, we can indicate water vapors as a gas. Here is a typical problem if we solve using the ideal gas equation of states. The compressed air tank have volume 0.84 cubic feet, temperatures 70 degrees Fahrenheit, atmospheric pressure is 14.7 psi, and this one the absolute pressure. So you may say that the pressure is 14.7 psia. When filled, the gas pressure indicates 50 psi. So the question is, what is the density of the air? And what is the mass of the air in the tank? This combines the ideal gas law with density definition. We will work through the solution next. Here the solution for the problem set up in the previous slide. In this case, we use the ideal gas equation of state for air to evaluate the densities of the air at the specific temperatures and pressure. And after that, based on this density, we can evaluate the weight of the air. This example is processed in your textbook. All the concepts and definitions of thermodynamics properties are included here for your reference and also used in this course as well. Density rho is the mass per unit volume. And the specific volume, in this case small v, is the inverse of density. So the volume per unit mass, specific gravities compare substances density to those of water. And specific gravities is the ratio of the density of that substances compared to the densities of water. Look at the table. Water have a specific gravity equal 1. Mercury is 13.6 and very dense. And air is 0.0013, so very light. Specific weight, gamma is the weight per unit volume. So we can use those definition and concept in our fluid mechanics calculations.